Hey guys, welcome back. We're going to do another one here. This is the same handout, Unit 3, Handout 5, number 6. Okay, and I chose this one because this one we're correcting the power factor to 90%. So I'll have a look, another handy circuit here where I don't have to calculate the current or the power factor given, okay? So this is a power factor correction question, so I'm going to draw a uncorrected. All right, guys? That's how we start all of these power phasor or power factor correction questions. Uncorrected, and I know it's going to look like this. I don't have to worry about it too much. Just draw a triangle. I know my power is there, my VA is there. My VARS is there, my power factor is here. My power factor is equal to 0.6, so I'm going to put that in there, all right? And once again, I've given you the current and the voltage, so you can multiply those together. They will equal your VA. So your VA in this guy is going to be 208 times 20, okay guys? 208 times 20, 4160. Volt amps, okay? And the next thing we're going to do is calculate our power. It is going to be our VA times the power factor, okay? Times 0.6, 2496 watts, okay? The last thing I'm going to do is calculate my VARs. It's going to be 4160 squared minus 2496 squared, square root. So it's going to be 4160 squared minus 2496 squared equals root equals. Looks like our reactive power is 3328 bars. Okay, and now that I've completed this entire drawing, I'm going to move on and check to see what's going on here. We need to figure out the capacitor required to correct this thing to 90%. So we're going, just like the unity one, we're going to draw a corrected power phasor diagram. In this particular case, you need a phasor diagram. Like I talked last time about, if we were correcting the unity, guys, our capacitor would be 3328, right? And our VA would be 2496. It would look like this. And VA would be right there, right? But we're not correcting the unity, correcting 90%. So we are going to draw this one here. And just like the unity one, there's nothing I can do about the true power. It's 2496 watts. It's going to be there, and that's all there is to it, okay? And actually this VARS, which is VARS XL, big inductor in this motor. Big winding, right? This is going to be my VARS XL, okay, and it's 3328 VARS. And that's sitting right there. Now, our capacitor that we're going to connect in parallel here is going to start here and go down. Now, if we were correcting the unity, it'd go all the way down, right? But we're not correcting the unity, we're correcting it 90%. So we're going to take care of some of the reactive power and leave some. Okay, so this is going to be our cap, okay, guys? And this line right here is going to be the sum of the three, and it's going to be our VA after correction, okay? And what we're trying to do is correct this to 0.9, which means we're going to leave this, which is going to be our VARS X, okay? When you correct a unity, there is no VARS X. You've taken care of all the reactive power with a cap. When we're correcting at 90%, we're going to leave some reactive power in the circuit, okay? And that's going to be our VARS X. Now that I've done this, I can start to try to figure it out. Now I know my power and I know my power factor. It means I can calculate my VA because the power factor, as you guys are aware, is P over VA. And here we had our VA, we were calculating our power. So our power was our VA times the power factor. In this case, we know our power, we're calculating our VA. If I transpose this question, it's going to be the power over the power factor, okay? And so it is going to be the 2496 over 0.9. And 2496 divided by 0.9 equals, looks like it's 2773 volt amps, okay? So that's going to be our VA after correction. And now that we know those two, I can calculate this one. It's going to be 2773 squared minus 2496 squared. Okay, so I'm just going to do that. Squared minus 2496 squared equals root equals, looks like this is 1209 vars. Okay, now that is not the capacitor. Okay, that is not the answer to A. That is the reactive power in the circuit that we're going to live with. The capacitor is that little green line there, okay? And you can see that the capacitor is going to be 3328. It's going to be the vars that we started with, okay? The reactive power due to the inductor minus the vars we're going to live with, all right? So the cap, guys, is going to be equal to 3328 minus 1209. Let's do that. 3328 minus 1209. It is 2119. 2119 vars. Okay? And that right there, guys, is the answer to A. Okay, guys? If we were correcting the unity, it would be 3328, right? But we're not correcting the unity. Now, a lot of students, you know, they do this right, they do this right, they calculate that, then they calculate this, and then that's the answer they give me over here, okay? They give me 1209. And that is not the capacitor. That is the reactive power they're going to live with in the circuit. All right, guys? So the capacitor is the vars of the inductor minus the vars that we're going to live with. Okay, guys? Now, rudely, this one's asking for the value of that capacitor in microfarads, and I'm going to show you how to do that, okay? And it's going to take two formulas, and there's more than one way to do this, guys, and maybe you learned it a different way last year. I don't know. I wasn't your teacher, okay? But I'm going to show you the Van Andel way, all right? And the Van Andel way uses this formula right here that you learned in level 1. It's this one right here. P is equal to E squared over R. Okay, that is one of the power formulas we learned in level 1. But I'm going to rewrite it for, you know, the reactive power, which is vars is equal to E x squared over x. All right, so that's the formula we're going to use. Now, the reason I want to use that formula is because it's going to allow me to calculate XC. In other words, this is our capacitor, 2119, okay? But I want to know how many ohms that is. Because if I know how many ohms it is, you know, maybe I can figure out how many microfarads it is. So if I transpose that formula for XC, I end up with XC is equal to E squared over vars, okay? So this is step 1, is to apply this formula right here. XC is equal to E squared over vars. Now E squared is 208 because this motor, guys, looks like this, right? It's a resistor and an inductor, right? And we've just added a capacitor for power factor correction. And if this guy was 208, okay, then that capacitor is getting 208. So it's going to be 208. I can just take, you know, the voltage. It's going to work every time. Over the vars of the capacitor, 2119. Let's do that for a second. 208 squared divided by, divided by 2119. And it looks like this guy is 20.4 ohms, okay? And that is XC. And the reason I wanted to calculate XC is so that I can apply this formula right here, which is XC is equal to 1 over 2 pi FC, because I want the value in microfarads, and that formula that I can use to calculate it needs the value in ohms. I have to transpose this formula, so it ends up being C is equal to 1 over 2 pi F XC, okay? And so this is step 2 of the Van Andel way. First step is to figure out how many ohms it is using this formula. XC is equal to E squared over vars. Second step is to figure out how many farads it is using this formula. C is equal to 1 over 2 pi F XC. So C, guys, is going to be 1 over 2 times pi times 60 times XC, 20.4. All right, guys, and let's see what that is. 2 times pi times 60 times 20.4 equals 1 over x equals. It looks like it says 1.3 times 10 to the minus 4, which is 0.00013 farads, which is 130 microfarads, okay? And that there, guys, is the answer for B. Okay, guys? Real quick, I'm going to calculate these other two. What would be the new value of line current? Well, we already know that I is equal to VA over E. And the VA after correction is 2773. And the voltage is 208. I is always going to be equal to VA over E. 2773 divided by 208. 13.3. Okay, down from 20. This thing was drawing 20 amps before I corrected it. Now it's drawing 13.33 amps. Okay, so I've done two things. I've improved the power factor, not to 0 degrees, okay, but 90.9, which is about 25 degrees, roughly. All right, which is good enough, right? No penalty. I've also reduced the circuit current to 13 amps. Now, draw a schematic showing the circuit components. I'm going to do that right here, okay? We're going to draw a circuit, a schematic for this circuit right here. All right, guys. Now, if you look in the back of the book, you can see it, but I'm going to draw it here. I've already just kind of drawn it up here, right? Here's our motor, guys. And here's our capacitor that we just added in parallel. All right. Now, this guy is 2119 vars, right? And here's our 208 volts supplying this circuit here, okay? Now, we know that the circuit current before correction was 20, right? So if I clamped on right there, that guy would be 20 amps. Now, it's also possible for me to calculate this current right here. Excuse me. That current there, since vars is equal to EX times IX, then IX should be let's see, yeah, vars over EX. And so it's 2119 over EX, which is the voltage dropping across that, which is 208. So just for fun, I'm calculating this here. The current flowing through this capacitor, just so we can add it on there. Okay, so it's 2119 divided by 208. Looks like it's 10 amps. 10.2 amps right there. And guys, this current right here, 13.33 amps. Okay, so this circuit after correction would look exactly like this. And by the way, this motor would continue to draw 20 amps. It was drawing 20 amps before I corrected it. It doesn't even know about this capacitor. Okay, all it knows is it's getting 208. And if it was drawing 20 amps before correction, it's continuing to draw 20 amps after correction. The difference is the total circuit current is down now to 13 amps. And now this is where students go, listen, Van Andel, there's just no freaking way that I got 20 amps on this rung and 10 amps on that rung, and the current feeding those two is 13. But that is exactly what's actually occurring, guys, because what was happening here before, if I draw my phasors, current phasors, that 20 amps, guys, it was hanging around down here somewhere, okay? This is the I motor, okay, and it was equal to 20 amps, lagging the voltage by a lot because it's a big inductor, okay, guys? And what we've just done is added a capacitor. This is I, XC, really, okay, and it's 10.2 amps, and it's like leading by 90 degrees, so there it is. And then the phasor sum of the two, guys, is going to be I total, going to be that blue line right there. This is I total, and it's 13.33 amps, okay? And you'll notice that it's still lagging because we corrected this thing to 90%, okay? So it still lags a bit, okay? But you can see here that the total current is less than, even the motor current. And that's because the motor current was lagging so much. And we fixed it with a capacitor, made it lag less, and also reduced it. Okay, guys, so sorry that this video is a little longer than some of the other ones, okay? But we'll take up some homework next week. All right, guys, have one. Have a good one.